ask myself, why am I attracted by the outside of the turn?
I think it's the centrifugal force.
Oh, never heard of that.
So, coming back home, I was still asking myself the same question and searched for more explanations. Let me develop. Calling that phenomenon the centrifugal force was actually a huge mistake. It's not the centrifugal force. By the way, this force does not exist. What makes us feel attracted by the outside of the circle is the reaction of the centripetal force, but we'll come back to that later. So, the centripetal force is the net force that acts on an object to keep it moving along a circular path. Any object traveling along a circular path of radius r with velocity v experiences a non-zero acceleration even when v is constant. Thanks to Newton's second law F equals ma, this non-zero acceleration implies a force that we call the centripetal force. The acceleration vector within a uniform circular motion is directed towards the center of the circle, thus the centripetal force as well. To be a little more precise, let's have a look to this print screen. With a constant velocity, here is the velocity vector of the car tangent to the circular path. A little further, the velocity vector of the car will be directed like this. If we calculate the resultant vector, delta v, we can observe that it is directed toward the center of the circle. Moreover, we know that A equals delta v over delta t. Thus, the resultant vector is equal to the acceleration during a certain time. Since F equals ma, the force is directed towards the same point as the acceleration. Thus, the centripetal force is the force directed towards the center of the circle. In order to understand this concept, we have to clearly understand what is an acceleration and when it appears. By definition, an acceleration describes the rate of change of velocity with time. It means that if there is a change of the velocity vector during a certain time, there is an acceleration. The acceleration formula is thus A equals delta v over delta t. As an illustration, let's begin with the car on a straight line. Have a look here. Here, when we realize we are late for mechanics class, we hurry to the car. Morgan steps on the gas. At the very moment the car accelerates, our body are pushed through our seats. So this is the consequence of the first Newton's law. A body that is in motion wants to stay in motion with the exact same speed. It is a reaction to the acceleration of the car. Here, the car has an acceleration because the magnitude of the velocity vector of the car changes. The acceleration vector is a tangent to the velocity vector. That was for the linear acceleration. Let's see now what happens when the car goes through a circular path. When we are in two dimensions, a change of the velocity vector can be a magnitude variation, as the previous example, as well as a direction variation. This means that the acceleration vector has two components, one when the magnitude of the velocity vector changes, and one when the direction of the velocity vector changes. We call it the parallel component when there is a magnitude change. This one is tangent to the velocity vector. When there is a change of direction, we call it the radial component, which is this time perpendicular to the velocity vector. Another thing, when the body follows a circular path where the magnitude of the velocity is not constant, 4 accelerations are applied on the body. First, let's talk about the parallel component of the acceleration. It appears only if the turnstile has a change of magnitude in its velocity. As we see on the picture, the origin of this acceleration is the angular acceleration of the turnstile, and its direction is tangent to the circle. Its magnitude is omega dot u. Let's now imagine that the person on the turnstile moves and goes to the center of it. The acceleration that she will measure on the turnstile and the acceleration that we, outside the turnstile, will measure will not be the same because we are in two different inertial frame of references. This is what we call the relative acceleration. The magnitude of the acceleration is measured as x dot dot. We can now talk about the Coriolis acceleration that appears when someone on the turnstile throws a ball to someone at the opposite of the turnstile. As the ball has a constant velocity relative to the mobile reference, a fictitious force is applied on it and will thus derive it from its initial straight path regarding the mobile frame, as we can observe on the image. The direction is tangent to the circle, if the person has a radial velocity, which is the case here. The magnitude of the acceleration is 2 times omega x dot. And we can finally talk about the centripetal acceleration, which is the most important one here. The centripetal acceleration appears even if the magnitude of the velocity is constant. Along a circular path, the velocity vector changes instantly of direction because it is always tangent to the position vector. As there is a change of direction, we have thus a radial acceleration, as it was explained earlier. This is why a body has a non-zero acceleration when it goes through a circular path with a constant magnitude of velocity. The acceleration vector is perpendicular to the circle and directed towards the center of the circular path. The magnitude of this acceleration is omega squared multiplied by u. Thanks to this acceleration and the second Newton's law, F equals ma, we have the centripetal force, which is also directed towards the center of the circle.
But I have still last question. Regarding the different parameters of a force, how does this one change?
Here is a truck transporting a shelf. The truck has an acceleration of 1.5 radians per second squared during 2 seconds. Afterwards, it keeps evolving around the roundabout at a constant speed. We said earlier that when you're sitting in a car that follows a circular path, you feel pushed towards the outside of the curve. This is exactly what happens here with the shelf. As the truck evolves around the roundabout, the shelf inclines towards the outside of the curve. You can also see an arrow in the animation. This is the centripetal force. According to the equation, the centripetal force gets bigger as the car accelerates, and so does the representing arrow. The centripetal effect is not just some physician invention. It has a great importance in several fields such as aeronautics, roller coasters, and in the automotive industry. In this video, we focus on automotive applications, and we therefore went to a karting center. Indeed, when a kart follows a circular path, the centripetal force acts as the force allowing the vehicle to turn. In fact, it is related to the friction force exerted by the tires on the road. Let's analyze what we just saw with the kart in details. To make it easier, the same phenomenon is illustrated here with a bike. As we explained in the illustration with the truck and the shelf, the arrows represent the centripetal force. When you turn your steering wheel, you create a slight difference in radius. Indeed, the curved trajectory followed by the front wheel has a smaller radius than the one followed by the back wheel. As the centripetal force equals v squared over r, this leads to a difference between the two wheels in the magnitude of their centripetal acceleration. Therefore, the force on the front wheel is bigger than the one on the back wheel, and the bike then starts to follow a curved path. So what happens when you make a car spin out? Well, when you drift, it is obviously because you arrived at a too high speed to take a turn. As a parallel, let's analyze what happens when the bike evolves at a higher speed. Before analyzing the animation, just a quick explanation of an important graph: the evolution of the friction force depending on the centripetal force. We can see on the graph that when you go beyond a centripetal force, the friction force reaches a peak. As a result, you move from a static state to a kinetic one. The kinetic state is the one that causes your bike to slip on the road. If you look at the video, you can see that the increase in centripetal force caused by a higher velocity moves the bike to the kinetic state, and it starts to slip. A last interesting case happens when the bike's back wheel rides over a puddle. In this case, it is not the centripetal force that causes the bike to slip, but it is the difference in friction coefficient of the two wheels. For the same centripetal force, the back wheel has a friction coefficient smaller than the front wheel, so the back wheel starts to slip and the bike follows.
Last but not least, I was talking earlier about the centrifugal force. I would like to explain more about this phenomenon. Even if it seems weird, we can't talk about a centrifugal force because it simply does not exist. If there was an outward force that was against the inward force, the centripetal one, it would mean that the body is in equilibrium, and that's not true. First of all, the body moves through a circular path, and because its velocity constantly changes in direction, the body has an acceleration. Thus, it is not in equilibrium. Besides, if there was an outward force that balanced the inward force, the body would move in a straight line and not in a circle. You still wonder why you feel pushed outside the car while driving a roundabout? The answer is simple. When a car is in a roundabout, there is a centripetal force that allows the car to follow the circular path. But this force is not submitted to people who are in the car. Thus, thanks to the first Newton's law, they want to follow their straight path as they are in the inertial frame of reference.